Welcome to the lesson on root cause analysis tools. Upon completion of this lesson, learners will be able to identify different root cause analysis tools, discuss the advantages and disadvantages of each type of root cause analysis tool, and assess when certain root cause analysis tools would be applicable. If your company wants to conduct root cause analysis, how would you start? What steps do you have to take? What tools can you use to determine the root cause of your production problem? In this lesson, we will describe some of the different tools that are used in root cause analysis, the pros and cons of each tool, and when each tool would be applicable. Several root cause analysis tools can be used to identify and address underlying issues. Fishbone diagrams, Ishikawa, help visualize potential causes by categorizing them into critical areas, while Pareto charts prioritize issues based on their frequency or impact. The 5 why analysis digs deeper into problems by repeatedly asking why to uncover root causes. Failure modes and effects analysis, FMEA, assesses and prioritizes potential failure modes based on their severity and likelihood. Fault tree diagrams, and FTD, map out cause and effect relationships in complex systems, and scatter diagrams help identify correlations between variables. Finally, the design of the experiment, DOE, allows for the experimentation of variables to understand their effects on processes. These tools can be used individually or together to identify and solve problems effectively. A fishbone diagram is a visual representation of the cause and effect relationships of multiple workplace elements. These diagrams are sometimes called cause and effect diagrams, but are more commonly called fishbone diagrams because their shape resembles fish bones. The head of the fish is the problem you are looking into, and the bones of the fish are the possible factors. Typically, there are 6 categories of elements or factors used in fishbone diagrams. They are equipment, processes, people, materials, environment, and management. Each one of these categories is investigated to determine if they contributed to the problem. Fishbone diagrams are particularly helpful in starting the root cause analysis process. They can be used as a brainstorming or creative thinking method where ideas are listed and organized. Tool to produce ideas of where to start the investigation of the problem. Fishbone diagrams are also helpful for projects where it is not possible to collect a large amount of data on the problem. This diagram can be used to show cause and effect relationships and how they led to the problem. The biggest drawback to using fishbone diagrams is that they cannot show the level of contribution of each factor to the problem. They can only show connections. Through the use of a fishbone diagram, you cannot determine which cause plays the biggest role in creating the problem. So, fishbone diagrams are helpful in determining what potential causes are, but not determining the cause that is the most problematic. A Pareto chart is a graphical representation of data collected on the causes of a particular problem. It shows how often a problem is created from a specific cause and can tell you which cause creates the most effects. This chart is especially useful in identifying the most significant contributors to a problem. In this example of a Pareto chart, 6 potential causes could create the problem being analyzed, numbers 1 to 6. The orange bars show the count of the number of times that cause created the problem. For example, about 70 defects were produced due to cause number 1. The purple line shows the cumulative percentage, adding all the previous percentages together, of the number of defects or problem occurrences. Pareto charts are commonly used in quality control, customer complaints, and process improvement to focus efforts on the most impactful causes. To build a Pareto chart, the first step is to collect numerical data by recording each defect and its cause and identifying the contributing factors. This data is typically organized in a Pareto worksheet, categorizing the causes and defect counts. Next, tally the defects for each cause, calculate the percentage each cause contributes, and determine the cumulative percentage. Finally, the data will be arranged in a chart displaying the causes in descending order and adding a cumulative percentage line to highlight the most impactful causes. This chart provides a clear, prioritized view for targeted analysis and decision-making. There is a theory called the 80/20ths rule for Pareto charts, which states that 80% of all problems are usually produced by only 20% of the potential causes. This rule implies that you can reduce the number of defects dramatically by addressing only a small number of critical causes. You can determine which causes are in this 20% by looking at the cumulative percentage line on a Pareto chart and finding the 80% mark. All of the causes that add up to 80% would be the causes that you should focus your improvements on to make a dramatic change in the number of defects. So, in the example Pareto chart above, the causes to focus on would be cause 1 and cause 2. Pareto charts are effective tools for telling you which causes occur most often. However, Pareto charts cannot take into account defects that are generated by a combination of factors and causes. Each defect must be put into a cause category and cannot be classified as having multiple factors involved. Overall, Pareto charts are a helpful tool in root cause analysis, but they require a large amount of data to be collected, which can be infeasible for certain projects. This tool should be used if data on defect causes is readily available or easy to collect. Let us now take a look at the next method, the 5 why analysis. This is a method of exploring cause and effect relationships until a root cause is determined for a problem. The method for completing 5 why analysis is basically to ask the question why something occurred until you find a true cause. It typically takes around 5 iterations of asking why before you reach the root cause, hence where the name comes from. Here is an example of 5 why analysis. The problem is that my car will not start. Why 1? Because the battery is dead. Why 2? Because all of the power was drained. Why 3? Because the car light was on all night. Why 4? Because the car door was not closed properly. Why 5? Because I had my hands full of groceries when I got out of the car yesterday. In this example, the root cause is a simple human cause created by a distraction. The driver was getting their groceries out of the car. 5. Why analysis is a good root cause analysis tool that is simple to apply and can help you determine a root cause quickly. Because it is a simple analysis tool, it can be used to help solve many different types of problems or scenarios. Like the fishbone diagram discussed previously, 5. Why analysis is commonly used when it is difficult to collect numeric data on the causes of the problem. The main problem with the 5 why analysis is that it is only as accurate as the people you're gathering your information from. Typically, you will ask employees about experiences that happened in the past, and so you are relying on the quality of their memory to determine a cause. Failure modes and effects analysis, abbreviated as SYN-EV-QEM-MT, is a root cause analysis tool that determines the likelihood and severity of a system or product failing. The system or machine is observed to determine all the possible ways in which it could break or fail, called failure modes. A failure can usually be detected because of its failure effect, which is the physical change seen due to a failure. The goal of FME is to determine which possible failure modes are the most harmful, either because of their severity or because of the frequency with which they occur. Once the critical failures are identified, improvements can be made to the system, so these failures are less likely to happen. The first step in using FME is to create a list of possible failure modes for the system in question. Next, for each of the possible failures, you must determine the severity of the failure, the probability of it occurring, and the likelihood of detecting the failure if it occurs. Each of these 3 categories is given a score from 1 to 10, with 10 being the worst, and then the scores are multiplied together to determine the risk priority number. The different failure modes are then compared based on their risk priority number to determine which mode is the most detrimental. This failure mode would be the one to focus on for further improvement projects. Here is a graphical representation of the steps for failure modes and effects analysis. You start at the top of the circle and follow the steps in a clockwise direction, determining a severity score, a probability score, and a detection score for each mode. Then you multiply them together to get a risk priority number for each mode. These risk priority numbers can then be compared to each other to determine which cause of failure is the highest priority. FME can be used to analyze any system or product in any state, but it is most effective to use during the design phase of a new system. This way, failures can be detected before they cause large problems and can be easily changed since the system is not fully implemented yet. One disadvantage of FME is that it cannot be applied to complex failures that occur because of problems in multiple different systems. It is typically just used for solving problems within one system or machine. A fault tree diagram is a graphical representation of the flow of events that leads to a system failure called the top event. A fault tree diagram shows the cause and effect relationships between events that eventually lead to the problem in question. Each event is represented by a shape, a circle, a diamond, an oval, a square, etc., and all the events are connected by logic gates. The logic gates represent the relationship between the event causes and the result. An OR gate means that only one of the events connected to it must happen to cause the resulting event. An AND gate means that all of the events connected to it must occur to cause the resulting event. Through the combination of these events and gate symbols, a system of events can be represented. Because the diagram uses logic gates, it is possible to represent a complex system where multiple factors lead to the occurrence of the top event. The major problem with fault tree analysis is that it cannot represent the extent to which an event causes the top event. It can show connections and relationships, but not which event or events play the major role in causing the problem in question. Scatter diagrams are charts that show relationships between two factors or events. The diagram represents each data point with a dot on the chart, and patterns are found within the data. If there is a pattern in the dots, then it proves that there is a correlation between the factors. A correlation is any pattern discovered in data that suggests dependence between variables. A correlation does not always prove causation, the situation when one event always causes the occurrence of another event. There are two main types of correlation, positively correlated and negatively correlated. An example of two positively correlated events is the number of cups of coffee a person drinks and the number of hours that person stays awake that day. As the number of cups of coffee increases, so does the average number of hours a person stays awake. An example of negatively correlated events would be a student's GPA and the number of hours they spend watching television. As the number of hours watching television increases, the average GPA decreases. Each of these correlations proves that there is some relationship between the two factors, but it does not prove that one factor causes a change in the other factor. Scatter diagrams are helpful in root cause analysis because they can be used to determine if certain factors affect events. They are relatively easy to create and do not require large amounts of data to show a correlation exists. The biggest problem with scatter diagrams is that they cannot show the root cause of a problem, only the relationships between two factors. They also cannot take into consideration complex problems that are caused by multiple factors. When you are investigating a process that has many factors that influence it, you need some way to determine which factors are important and which are not. The design of experiments is a series of tests in which changes are made to different factors to observe their effects on the process. By controlling the factors of a process, you can determine which factors cause the problem you are investigating. Let us now discuss the various steps in the design of experiments. The first step in the design of experiments is to determine what problem you are investigating or the quality characteristic. An example could be investigating if stamping process factors affect car body panel fitment accuracy and surface finish quality. Next, the factors that could affect this quality characteristic are determined. The factors for this example could be the stamping press pressure, material temperature, sheet metal thickness, die clearance, lubrication level, and press speed. The third step is to define the levels at which each factor is going to be tested. For this example, the levels could be the following: press pressure, 800 tons or 1,000 tons. Material temperature, room temperature 20 degrees Celsius or preheated 35 degrees Celsius. Sheet metal thickness, 1.2 millimeters or 1.4 millimeters aluminum. Die clearance, 0.1 millimeter or 0.15 millimeter gap. Lubrication level, standard or enhanced application. Press speed, 12 strokes per minute or 15 strokes per minute. Next, an experiment must be created to represent every possible combination of factors and factor levels. The next slide shows an example of stamping process factor combinations. The table here shows a partial factorial experimental design with 8 runs out of a possible 64 combinations in a full factorial. Each row represents a unique combination of factor levels. Runs are organized to test different interactions between factors. The table includes both high and low levels of each factor. Typically, the experiments should be done in a random order to avoid additional influences on the data collected. For each experiment with its own unique set of factor levels, data is recorded. After the data is recorded, statistical analysis can be done on the data to determine which factors are truly affecting the process. Design of experiments is an effective root cause analysis tool because it statistically proves which factors are causes of the problem you're investigating. The main problem with design of experiments is that it becomes extremely complicated in situations that have large numbers of factors and factor levels. Also, it can be costly to run enough experiments to get the statistical data required for the analysis. In summary, various tools are available to identify the root cause of a problem, including the fishbone diagram, Pareto chart analysis, 5Y analysis, failure modes and effects analysis, fault tree analysis, scatter diagrams, and design of experiments. Each of these tools has its strengths and weaknesses. Some tools require more data and are highly accurate in pinpointing the actual cause, while others need less data but may need to be more precise. No tool is universally better than the others. Each one works best in specific situations. Selecting the right tool or combination of tools can address problems more effectively and uncover the root causes. Thank you.